Okay, so this is the screencast for my Mousetrap car project, and here is the video of my car.
So, straight roll.
Okay, so as you can see, the car moved from right to left, which means that my car was moving in the negative direction. So, to find the energy stored in the spring, we did this. And this is a rough sketch of the graph that we got from the Trojan wheel. And to find the spring constant, we had to find the area under this graph. So we split it into two parts, this rectangle and this triangle. So for the rectangle, to find the area, it's base times height. So the height is 1.092 newtons, and then the base is 0.06 pi meters. So 1.092 times 0.06 pi is 0.206 joules. And for up here, to find the base, down here we did the slope of the entire graph, which is 27.17 newtons over meters, times the base, 0.06 pi meters, which equals 5.12 newtons. So, since the area of a triangle is found by 1/2 base times height, we did 1/2 times 5.12 times 0.06 pi, which equals 0.483. So to find the spring constant, we just added 0.206 plus 0.483 joules, which equals 0.689. And down here, all we did was we added 5.12 plus 1.092 newtons to find 6.212 newtons of force from our graph. Okay, next we have our position over time graph, which we found from the data from Tracker. So down here is the position time graph, and as you see, we have a parabola. So we did a curve fit. So right here, the curve for the car speeding up, for RA, which we found from dividing our slope from the velocity time graph when it was speeding up, which we found to be negative 0.8446 divided by 2, which gives us our A value down here, negative 0.4223. Our B value is the same as the y-intercept value up here, which is 2.883, and our C value is negative 4.9 to fit the curve. For this second curve, when the mousetrap is slowing down, once again we divided our slope by 2. So 1.499 divided by 2 gives us our A value of 0.7495. Our B value, same as the y-intercept, negative 10.94. And our C value is 35.80. Okay, so next we have the displacement of our mousetrap, and displacement is found by our x final minus our x initial, and x meaning position. So our x final is negative 4.0425, and our x initial is 0. So that means our displacement is negative 4.0425 feet. Sorry, that's supposed to say feet, not meters. Okay, so next we have the mass of our mousetrap car, and this is the rough sketch of our graph. And the force, the mean that we're going to use to find the mass is 1.666 newtons, and then we times it by 1 kilogram over 9.8 newtons, which is the normal force on objects on Earth. So for every 9.8 newtons So, okay, for every 1 kilogram, there is 9.8 newtons acting upon it, so which means 9.8 newtons equals 1 kilogram. So to find the mass, we did 1.666 newtons times 1 kilogram over 9.8 newtons, which would cancel out our newtons to leave us with kilograms, and the answer is 0.17 kilograms for our mousetrap. Okay, so here on this graph, we found the maximum velocity of our mousetrap car, and we did analyze model statistics for the data set. And since my car was moving in the negative direction, we're going to use the minimum value for my maximum velocity, which is negative 2.207 feet per second. Next, we have the kinetic energy of our car, and the equation is kinetic energy equals 1/2 mass times velocity squared. So we have EK equals 1/2 times 0.17 kilograms times negative 2.207 feet per second squared. Feet per second. That's the units for our velocity, not meters per second. Sorry. So we have down here 0.17 divided by 2 times negative 4.870849, which gives us our answer of negative 0.414 joules of kinetic energy. Okay, next from this graph, we are going to find the acceleration. So we did the linear fit for when the car was speeding up, and the acceleration is negative 0.8446 feet per second squared, and the acceleration for when the car is slowing down is 1.499 feet per second squared. Next, we have the force diagram of our car. So when it is speeding up, we have the weight of the earth, gravity pushing down, and we have normal force of the surface pushing up. And then we have the force of the surface on the car, or the friction. And in this case, the friction from the surface is causing the car to speed up in the negative direction, which is why this force is facing to the right. Okay, down here we have our vector diagram, and as you can see, the normal force equals the weight, and down here we have the friction going to the right, and up here we have our total force vector, and total force, or sum of forces, is found by mass times acceleration. So since our sum of forces vector equals our friction vector, this means that friction equals mass times acceleration. So we have friction equals 0.17 kilograms times negative 0.8446, which we got from the acceleration when the car is speeding up, and our answer is negative 0.1436 kilograms times, our friction is kilogram times meters per second squared, and which means that our total force for when it is speeding up is negative 0.1436 newtons. When the car is slowing down, this is the force diagram. We have the weight of the earth and the normal force pushing up. And this time, since the car is slowing down, we have the friction from the surface going to the left. Over here, we have our vector diagram. This time, the friction is on top, going to the left, and down here is our sum of forces vector going to the right. same as the this part, the friction equals our sum of forces, which means friction equals mass times acceleration. So for this part, we have 0.17 kilograms times 1.499 feet per second squared, feet, which we found from the graph. So the answer is 0.25483 kilograms times meters over second squared, which means our total force is 0.25483 newtons. Okay, so this is the energy flow diagram of the car moving. Our first part in motion is when the string, or this is wound all the way around the back axle, which means that this car has elastic energy and its velocity is 0. So we have elastic energy right here. And then we have the system, which is the Mousetrap car, and during its motion, there is dissipated energy. So we have elastic energy minus dissipated energy. And our third part in motion is when the car is at its maximum velocity, which is defined by kinetic energy. Okay, so continuing on, this third part in motion is when the car is moving and the spring loses its elastic energy and it now has kinetic energy because it's moving and it has maximum velocity. So if we isolate E dis on one side of the equation, we have E dis equals elastic energy minus kinetic energy. And we found our elastic energy from the spring constant. And we found kinetic energy for the car. So we have E dis equals 0.689 joules minus negative 0.414 joules, which gives us a total of 1.103 joules of dissipated energy during the mousetrap's motion.